met him when he was a graduate student at the University of Düsseldorf, talking with him about what the right way was to model how to change people's votes, a subject that is of great interest to many Americans. We have a 501c3, I won't say which way. Dr. Erdélyi did his PhD in Düsseldorf, then went off and did postdoc at one of the what? No, NTU, which is okay, Nanta. What he said in Singapore. Is that what my friend was?
I think so.
Oh, okay.
Who
Now,
was? It was the question.
Erdélyi.
Okay, so I would say.
so apparently not where one of our recent graduates, not so recent
The question
graduates
is,
was.
do you know Jackson Japan?
No,
Okay, different.
different one.
So, Dr. Erdélyi will be talking to us about preferences and manipulation in elections.
Thank you so much for this introduction. First of all, I would like to apologize. I will chew on my chewing gum throughout the whole talk. It's not because I'm into chewing gums, but I got a terrible cold 2 days ago when I came to Kentucky. And if I don't have a chewing gum or candy, there's not coughing and can't stop. So, Professor Gold is always giving me candy in case I start coughing. I'm pretty sure I haven't even started my talk, but you already have questions. I already got one question before the talk. Where is Siegen? This is the first question I always got. It's the middle of nowhere, that's my answer. Because, as you can see, we are far away from Cologne, far away from Frankfurt, far away from Dortmund. But it's a nice thing, because the University of Siegen is specialized on medium and small enterprises, and our School of Economic Disciplines has a very strong connection to all these enterprises, and this is the area, one of the big areas in Germany where we have all these strong enterprises, and that's why University of Siegen is in the middle of nowhere, but still has a big area. So let's go to the talk. I want to tell you something about preferences and manipulative actions in elections. I will start with a brief introduction to the research area I'm working in. It's called computational social choice, and then I will go into a little deeper into voting theory and tell you a few things about manipulation, bribery, and electoral control in elections. I have prepared a few examples. I will start with from scratch from basic things. If it's too easy and you are familiar with all these things, let me know, then we can skip it forward and go into a bit deeper into other things. And at the end of the talk, if I have enough time, I would like to go into domain restrictions, because that's what's in right now in our area of research. So what is computational social choice? It's a pretty young interdisciplinary research area between social choice theory and computer science. And the main merits of computational social choices, I'll come to it in the next slide, is bringing together different research groups from different areas. For example, lawyers. You would think that they do things like that, but they do. In fact, my wife is a lawyer, and we have several joint publications within ComSoc journals and conferences. Economics people are interested in elections and outcomes of elections. Discrete mathematics, decision theory, theoretical computer science, and of course AI. So, as I already mentioned, the merits of ComSoc are that it contributes to both areas, both to social choice theory and computer science, by mutually transferring concepts between these two areas. For example, if we look at social choice concepts like preference aggregation or voting or collective decision making, we are all using them in computer science, computation planning, for example, in design of recommender systems. The other way around, what gives computer science for social choice? Well, for example, efficient algorithms or the complexity of problems related to voting. Why? There are several voting rules designed by social choice people ComSoc, I will now talk about voting theory, but there are also other areas, for example, preference aggregation. Difference between voting theory and preference aggregation is that in voting theory, if we aggregate the preferences of the voters, we only are interested in the winner of the election at the end. As in preference aggregation, if we aggregate the preferences, we are interested in the societal preference and not just the winner of the election. There's also resource allocation, fair division, coalition formation, and judgment aggregation, and belief merging. These are all interesting areas within ComSoc, and there are interesting lines of research for each of these topics. So going to preferences. Where do we need preferences? Almost every day, almost everywhere. For example, if we type in word into Google and we'd like to search for that, Google checks the options and gives us a list of results, which is basically a preference list, because the top result is, according to Google, the best option for us, and then the second one, and the third one, and so on. Basically, we have a list of preferences which gives us the best solution for our search word. Finding best solutions for problems, finding best appointments with other people assumes that we have several options and we are looking for the best one, so we have preferences over these options too. Political elections, of course, system configurations, multi-agent planning, and many, many more. So literally the application of voting and preferences is really fascinating. Now, if we are talking about preferences, we usually normally think of simple preferences. I like this better than that, or I like bananas more than apples, and so on. But they can be very complex. Here's an example for that. For lunch, we'd like to go out, and we have 4 options. Good Mexican fast food place 2 bus stops away. Nice pizza place for takeout 1 bus stop away. We maybe have a sandwich in the fridge from yesterday, so we don't lose any time. We just go grab it and eat it. Or we can go to a steakhouse, eat a nice juicy steak. It's around the corner, 5 minutes of walk. It's a bit pricey. So if you have to decide where to go, in this case we have several issues to consider. First of all, what kind of food would I like to eat? That's of course the basic question, because it's about lunch. But there are maybe other issues we have to consider. For example, ambience. Do I want to go to a fast food restaurant? Do I want to have a nice restaurant to sit in? Or is it fine if I just go and eat in my office? Distance can also play an issue. How far is it? How fast can I go there? So time machine here. And of course, if I have to take a bus, I have to pay for the bus. So even money can be an issue. As you can see, even for a simple decision, preferences can be very complex. Let's move to voting. Voting is a particularly useful framework for preference aggregation and collective decision making. While voting rules were originally used by political scientists, economics, social choice theorists, and operations research people, nowadays we find voting everywhere in computer science. For example, in AI, especially in multi-agent systems, in planning, in similarity search, and design of ranking algorithms, or the design of recommender systems, for example. If we have an election, how can we formally capture it? Well, first of all, we need a set of candidates, right? It's usually denoted by capital C. There's a finite set of candidates. We also have voters. It's usually denoted by V. I wrote there a good set of voters because it's possible that several voters have the same preferences. So basically the votes look the same for some voters. Now each of these voters has to give their preferences, somehow specify the preferences of the set of candidates. And this again can be done in several ways. For example, like preference lists. Here, each voter gives a ranking over all candidates, specifying first his favorite candidate, then his second favorite candidate, and so on under his least preferred candidate. This is with which I will work today mostly. There are also approve and disapprove vectors. So basically, each voter tells about each candidate, well, I like him, I don't like him, I like him, I don't like him, and so on. So basically, these ones and zeros to candidates. You can also specify so-called CP nets, which are conditional preferences introduced by Erdélyi and others in 2004. This is a nice way of specifying conditional references. So basically, there are some connections between different issues, and if issue 1, for example, we are going out for dinner, we are choosing fish over meat, then in the second step, if I choose a drink, I rather choose white wine over red wine. It's the other way around, meat over fish, then I choose rather red wine over white wine. I won't talk about CPNets today, it's just to mention it. We already have 2 faculty members here who already had nice papers and problems. The first ones studying CPNets, computational aspects of CPNets, Professor Bolis and Professor Chinsky. So if you want to know something about CPNets, and then we are the experts in this area. So let me show you an example how preference lists work, but it's really clear. We have 3 candidates, The Simpsons, The Big Bang Theory, and The ID Crowd. These are basically 3 TV shows. And we have 3 voters, or 4 voters, sorry, who tell their preferences over these TV shows. The Minion, the Lego Guy, Yoda, and Gábor Erdélyi. And for example, Yoda says his favorite TV show is The ID Crowd, his second favorite is The Simpsons, and if we had to choose between these 3, The Big Bang Theory would land on the last position. The set of all voters and all preferences is usually called a profile. Now, we have the candidates, we have the voters. How can we find the winners of the election? Well, we need a voting group, right? The voting group aggregates the preferences of these individual voters and outputs the set of winners. We distinguish between 2 models, the unique winner model and the non-unique winner model. The unique winner model, we only want to have exactly 1 winner or no winner at all, so we don't like ties in the top position. And in the non-unique winner model, we are allowed to have ties in the top position, so it's possible that we have 5, 10, or 100 winners at the same time for the same election. Now, what kind of voting rules do we have? There are many different ones, of course. You can divide it as you wish. But there are some prominent ones, like, for example, plurality and boredom. These are 2 voting rules. I will go into details later in this talk. These are easy, simple, so-called scoring rules, and scoring rules I will define a little later. There are also others like veto and pre-approval. These are also scoring rules. Then we have, again, different ones like Condorcet or Copeland, which are voting rules based on pairwise comparisons of candidates. And again, other voting rules, as far as I know, all these 4 orange-colored voting rules have a computationally hard inner problem. It means that even deciding if a candidate is a winner in an election, this voting rule, these voting rules is computationally hard. So, I mentioned earlier we had these several voting rules, scoring rules. The formal definition of it is given an election, E specified by a set of candidates and voters, and we have exactly M candidates in our election. We are given a so-called scoring vector, which is alpha 1 to alpha m, such that each of these alphas is a non-negative integer. Alpha 1 is greater than alpha 2, and so on to alpha m. And we assume that alpha 1 is strictly larger than alpha m. Then the score of a candidate C is the sum of scores he receives in each vote. And the winner of the election is the candidate with the highest score. So let's see a few examples. Plurality is a scoring rule. We are scoring vector 1, 0, 0, 0, 0. So basically, each voter gives his top ranked candidate exactly 1 point and 0 points to all other candidates. Example again, same voters, same candidates. If we use the plurality rule, then the Minion gives 1 point to the Simpsons, the Lego Guy and Yoda give 1 point to the ID Crowd, and Gábor Erdélyi gives 1 point to Big Bang Theory. So basically we have the scores 1, 1, and 2. second prominent scoring rule is the so-called order count. We have exactly m candidates, and the scoring vector looks like this. The top rank candidate gets m minus 1 point, the second rank m minus 2, and we are going like this. The last candidate receives exactly 0 points from each order. Same example. The scores look like this. The Simpsons gets 2 points from the Minion, 0 points from the Lego guy, 1 point from Yoda, and 1 point from Gargamel, summing up 2 plus 1 plus 1 plus 0 adds up to 4. You can check for all the other candidates the same. Each candidate has exactly 4 points. And if you are in a non-unique winner case, each of them are the winners of the election. So this is the last voting rule I'm going to introduce to you, the Condorcet voting rule, which is based on pairwise elections of candidates. So basically, the Condorcet winner is the candidate who beats every other candidate in the pairwise election. How does it work like? I made it a bit smaller so we can check everything step by step. We only have 3 voters here, but still this is 3 candidates. We now have to pairwise compare all the candidates. The first case, if we compare the Simpsons, the IT crowds, then IT crowd beats the Simpsons 2-1 because the Lego guy and Yoda prefer the IT crowd to the Simpsons, and the Minion prefer the Simpsons to the IT crowd. If you look at Big Bang versus the IT crowd, again, IT crowd wins because IT crowd beats in the second and the third vote the Big Bang theory. In the first vote, it's the other way around. So basically, the IT crowd beats both other candidates. Now he is the winner of this election in Condorcet. Now, as you can imagine, if we have something like this, we can end up in an election where we don't have a winner. It is called the Condorcet paradoxon. Basically, if we have some kind of cyclic ordering of these candidates, we can end up with the following result. The IT crowd beats the Simpsons 2-1. The Simpsons beats Big Bang Theory 2-1, and Big Bang Theory beats the IT crowd 2-1. So basically, presentation is not even here anymore, and right to that presentation. So we have no winner in this case. Now, as you can imagine, if you have different voting rules for the same election, applying different voting rules, you can end up with different results. If I take the original example we had, I have made a few slight changes. Then first applying plurality, the winner is the Simpsons with 2 points. Then applying order, the winner is Big Bang Theory with 5 points. For the same election, 2 different voting rules, we have 2 different winners. Now, there is an axiomatic approach to voting rules. You can define certain properties you would like to have. For example, if someone goes to the election and gives his honest votes, his preferences on the candidates, then you don't want the top-ranked candidate to get worse than if this guy wouldn't show, for example, at the election. So basically, you can define several properties like this and analyze voting rules, but I won't do this because it's not a topic I'm working on my research. I'm interested in the complexity of problems related to voting, especially manipulative actions. So, what exactly are manipulative actions in elections? We have an election. We assume that we know each voter's preferences over each candidate, so we have full information. I admit this is not really realistic, but right now let's start with that point. And there's an agent. It can be a voter, it can be an external agent, whoever, who is not happy with the outcome of the election, and he wants to do something to the election in order to change the outcome of the election. Now, there are many real-world scenarios where manipulative actions are possible, and we can also list a lot of examples cannot vote at all, right? So in the literature, we mainly distinguish between three different types of manipulative actions, so-called manipulation, bribery, and control. In manipulation, we have insincere voters. So basically, they know that if they vote insincerely, they will end up with a better result as if they would vote sincerely. In bribery, we have an external agent who has some kind of a budget and who wants to bribe a few voters, change their votes in order to reach his goal and make, for example, a candidate in the election. And the electoral control, we have again an external agent, the so-called chair, who can modify the structure of the election in order to change the outcome. At the end of the talk, I have a pretty long bibliography. I already sent the slides to Professor Goldsmith. You can maybe put the slides online so you can check the literature if you're interested in some of these topics. Manipulation was introduced, the computational complexity of manipulation was introduced by Barton and in the late 80s. Bribery was introduced by the group in Rochester in 2006, first paper on bribery. Electoral control goes back to Bartleby, Toby, and Tricky, and Bartleby and Worley in 1992. And there are two recent very good textbooks on computational social choice, not just on voting, but also on voting. The one by my PhD advisor, Jürgen Ruther, he edited the book, and the other one is by several guys from the consult community. It's a big book, it's really nice. The Ruther book is better for people who are not familiar with computational social choice because it starts from the scratch, gives many examples, and explains everything in detail. The other book is a little bit deeper, goes deeper into results, but both are nice to read, and you get a pretty good picture of what the research, actual research, what is happening. So, how can we manipulate an election? We have again our example. We are using board account as our voting rule. So basically, each voter gives his top rank candidate 3 points, second rank candidate 2 points, the third rank candidate 1 point, the last rank at 0 points. You have the preferences, and here are the results. So if we add up all the points, at the end, the ID crowd is the winner, 8 points, and Jaws is in the second position with 7 points. Now, Gábor, as always, he's not really happy with the outcome of the election, and he really wants Jaws to win the election. So what can he do about that? He somehow has to make sure that Jaws gets more points than the ID crowd, so somehow we have to move the score of ID crowd down below the score of Jaws. He can do that in a way that he can move the ID crowd from the second position to the last position, like this. In this way, the ID crowd loses 2 points, Big Bang and The Simpsons gain 1 point, Jaws score is unchanged. So at the end, we have 7 points for Jaws, ID crowd goes down to 6, and the others are also below 7. So basically, Gardner can successfully manipulate the outcome of the election. Now there's a negative result from the 70s, independently ruled by Gibbon and Semmelweis in 1975, which basically says that every reasonable voting rule and every reasonable election, that these 3 candidates can be manipulated. It's not good, of course, because we don't want manipulation of elections, but there's an answer to this negative result in complexity. What if we can find voting rules for which manipulation is although possible, because Professor Goldsmith says that it's possible, it is still computationally hard. This end, we defined these notions here. Immunity says that manipulative action is not possible in an election. Susceptibility says that a certain voting rule is not immune against manipulative action. We say that the voting rule is vulnerable to manipulative action if it is susceptible and the corresponding decision problem is solved in polynomial time. And we say that the voting rule is resistant to a certain kind of manipulative action if it is susceptible and the corresponding problem is computationally hard. Also the case with CPR. So we want to use worst case complexity as a shield against manipulation, but again, careful here, it's worst case complexity. It doesn't mean that NP hardness doesn't mean necessarily that for real life elections manipulation is hard. Because it's possible that we have some kind of a weird instance where we can show it is NP hard, but in all natural cases manipulation is totally easy. That is the first step. So here are the first results, computational results regarding manipulation in elections. Gábor Erdélyi and Trick showed that open alpha, maximum, and the whole class of voting rules, scoring rules, is vulnerable against manipulation. So basically the problem is solving all the time. This is not good. But they could also show 2 years later, Martin and Orlin, that there are voting rules, in this case single transferable votes, STE, where manipulation is computationally hard again. I would like to skip manipulation right here and go to bribery. I already mentioned how bribery works. We have a guy, external guy, who has some kind of budget and wants to change some votes. The formal definition is like this: given an election E, specified by a set of candidates and voters, non-negative integer K and a distinguished candidate C out of the set of candidates. The question is it possible to change and post K voters' votes such that our distinguished candidate C is the winner of the resulting election under voting rule X? You can look there and vote. Now there are several versions of bribery. You can have the standard version that is defined, yes?
So instead of giving them money, you might also think about spending time discussing issues with them or some other resource rather than dollars.
Yeah, but it's not time. And you have time issue, you need, I don't know, 5 units of time to convince this one, 30 to convince that one, you have 2 days. So you can also introduce prizes to the voters. This is basically that what we just mentioned, that each voter has some kind of prize, maybe money or time, whatever. If you have a budget, you can receive it. You can weight the voters. So one voter has a weight of 5, so his vote weighs 5 votes, the other one only 1. You can combine weights and prizes, and you can also introduce micro-bribery, where you basically have costs on each flip in each preference you want to change. So basically, you are not allowed to change freely the whole vote of the voter, but only some neighboring preferences become free. There are many papers on bribery in different settings for partial information, for full information, for weighted price, and so on. So the final model of manipulative actions is electoral control. Here, the chair seeks to influence the outcome of the election by changing the structure of the election. And we had this in 2000 presidential elections in the US, especially in Florida, where there were people listed on the register for elections, but they were not allowed to give their votes. So the basic idea here is changing the structure of the election, and here are options how we can do that. For example, we can add candidates to the election. If you think back that presidential election, George W. Bush was running against Al Gore, and there was a third guy, Ralph Nader, who basically stole the votes from Al Gore. That's why George W. Bush could win the election. Leading candidates, forcing candidates out of race. Imagine somehow they could have made Ralph Nader to get out of the election, get out of the race. In this case, probably Al Gore would have won the election against George W. But partition of candidates without runoff. Here we partition the set of candidates into two subsets. There's a qualifying round for some of the candidates. I know I'm in the US, I don't know if you're into soccer or not. The soccer world championships, usually the country who is organizing the world championships already qualified for the final round. All the other countries have to run through a qualification round, and only some of them are qualified for the final round. So that's the partition of candidates without runoff. Then we can also define with runoff two groups of candidates, each voter votes on both groups separately, and the winners move forward to the final round, and then we can determine the voting election. We can also add voters, these are vote rights. We can also delete voters, forcing voters out of the election, and we can also partition the set of voters, for example, using gerrymandering. These are all options of changing the structure of the election. A very powerful way doing that was done 2 years ago in Hungary, my country where I come from. The right-wing party was at that time also leading the country, changed the voting rules in Hungary in the way that they restructured the districts, so basically did kind of a partition of voters control, and also changed the voting rule from proportional voting to winner takes it all, basically plurality voting. And in this way, although they have only something like 40-something% of the votes overall, they won in each district. And basically went into the parliament to get more than 2/3 of the spots. Now these models I introduced here, they are going all back to the Bartlett-Tobian paper from 89, or 92, sorry. And some of them are natural, some of them are not really natural. So basically, if you think of the partition models, if you have a huge election, partitioning into two subsets is not really natural. There are many results, anti-harness results on this kind of partition of voters and candidates control actions. Most of them anti-harness results because partitioning into two subsets, you can always create some kind of weird instance where you have on one side one or two candidates, on the other side you create some kind of an exact cover of three sets or hitting set or whatever type of structure, and then you can immediately show anti-hardness. 2 years back when I visited Rochester Group around Punjab, we tackled this problem and introduced new partition models, basically not just partitioning into two subsets but into k subsets because it's more natural. We also wanted to have some kind of balance in it, so basically each of the subsets should be somehow